Hello everyone, welcome to another Lessons Learned video. Today we're going to talk about attacking ketones with nitrogen nucleophiles. If you didn't watch the last video, which I'll link in the description, please do, because there are some important principles there you want to know before you start this. But basically we take any ketone, we react it with a primary amine. So this has a methyl group and then two hydrogens. And then we basically take water out of the solution as it forms. And the product will be a double bonded nitrogen with the methyl group attached. You'll also get another version of it which will look like this. Now, here is the mechanism for how this happens. We saw in the last video that if you would use an oxygen nucleophile, you have to first protonate the ketone oxygen to make this ketone a good nucleophile, and then attack using the oxygen. In this case, you can just use the nitrogen to attack the ketone and it will work. You don't have to protonate the ketone first. So temporarily this is what you have. Now notice that in the reactant we have an oxygen, and in the product we have a nitrogen double bond to this carbonyl carbon. Essentially in this intermediate we have both of them, and so this is going to be a leaving oxygen and this is going to be a staying nitrogen in this case. What we need to do is take electrons from the nitrogen and bring them down here to form a double bond and kick out the oxygen. Now, of course, when the nitrogen is protonated and the oxygen is deprotonated, you can't really do that. We have to do some protonation steps before we get to that stage. So the first thing I would do in this case is protonate the oxygen. All right. So take, and your proton source is probably going to be a protonated amine. So take the same amine that we have using, but just add another proton to it. And then we can put the charges as a red so you can notice it more clearly. And then we can basically use that to protonate the the oxygen, which will become an alcohol group. Then in the next step you want to deprotonate the nitrogen, because we want it to form a double bond like this, but it needs some free electrons. Right now all of its electrons are in the bonds. So to deprotonate it we can use again an amine, because that's probably more abundant than anything else, and we take the proton and its electrons become a lone pair, and we can use that lone pair to later on form the double bond, but not right now, right? Later. So we get this intermediate. Now, let's scroll down. In this stage, we have electrons on the nitrogen, and theoretically we could do this. However, because we are in acidic conditions, it is easy and it's possible, and it should happen, that we should protonate the leaving group first. So the leaving oxygen, the OH there, should be protonated so that when we expel it, it becomes a water molecule, not a hydroxide. So first we need to protonate that guy. So what we do is we take another protonated amine. A protonated amine wouldn't have a lone pair left. And we take electrons from the oxygen, use it to attack one of these hydrogens. Now, when we take electrons from the nitrogen and bring them down, this leaving group is a water molecule. It's fairly stable, a lot better than if we had left hydroxide. All right, so now I'm going to draw this in an equilibrium arrow so you can bring up another point which I did in the last video as well. The leaving group was water, so we also get water as a byproduct. Now, this whole DS thing, Dean-Stark method, means that we take water out of the solution as it forms. So if we take water out of the solution as it forms, we're decreasing its concentration. The equilibrium will shift toward the left side to compensate for the decreasing amount of water. So we push the reaction toward the products. All right, now the last step, if you look at our product, it looks pretty much like what we have right now, except that we need to deprotonate it. So we take, you can use anything to deprotonate, just I use amines because they're more abundant in the solution. Just make sure you're reasonable with this and you will get the product. And of course, you will get a mixture of products, one where the methyl points left and one where it points right, because the ketone itself was initially asymmetrical. And this will be about 50-50. You won't have a minor or major product here. So let's do another example problem of this where we take let's take an aldehyde and react it with an ethyl primary amine. Try and predict what the product would be here. So the product here would be simply like that. Another way to draw it, you could say, is probably easier to see it that way. You're essentially taking out the oxygen, replacing with the nitrogen with the alkyl group attached. Right? Now, let's go back to ketones. It's the same with aldehydes, but these are primary ketones, meaning they have one alkyl group attached. It is also possible for that alkyl group, instead of it being an alkyl group, to be something else. For example, if you put OH here, you might think that that won't work because an OH is not similar to an alkyl group, and you are right that an OH is different than an alkyl group, but it'll actually work just the same, right? The reaction will proceed in the exact same way. So in other words, in the top example, we had an ethyl group, so we had an ethyl on the nitrogen, but now we have a hydroxyl, and this is a hydroxyl on the oxygen. So it will work just the same with alcohols, and again, same mechanism, except that you just have an alcohol there as opposed to an alkyl group. Now, the same is also true if you take this and you react it with a primary amine, where instead of an OH, you can have another amine, an NH2. And in that case, it will also work just the same. You will have the nitrogen, and you can guess that over here we would have the NH2 group. Now, there's a special utility to this type of molecule, because when we take it, and let me redraw the nitrogen-hydrogen bonds so that we can see the electrons. If we react this with hydroxide and heat, what we will get is simply nitrogen gas and an alkane. All right, now let's explain the mechanism for that. It's a bit of an unconventional mechanism, so you're probably not going to apply the patterns here to much other reactions, but you first deprotonate the nitrogen, and then let's show it simply. So let's do that. So essentially what happens is the nitrogen has now had a proton taken away, so it's negatively charged. Then what we want to do is we want to take the electrons on this nitrogen and form a double bond here. That means that this other one goes in and gives its electrons to the carbon. So the outcome is that this nitrogen-oxygen bond, well, nitrogen-carbon bond becomes single bonded as opposed to double bonded. This becomes a double bond because we just added electrons to it. And then we threw electrons on this carbon, so that carbon is now negatively charged. And then what we will do is we will go here, and this was really a resonance thing, so these two are the same molecule, except that the electrons is kind of spread out. The negative charge is spread out among the nitrogen and the carbon. But what can happen is that you can react this with some water that may be in the solution. And because carbon is very unstable thing you have a negative charge on, it will quickly steal a proton from this oxygen. So we will get the carbon will be neutral now. Now for the next step of the reaction, we have a lot of hydroxide ions still in the solution, so we can take those and use them to attack the other proton here, and then form the negative charge again on that nitrogen. Okay, then we do something funny. So we take the electrons in this nitrogen, bring them over to try and form a nitrogen-nitrogen double bond. Well, triple bond now. Then this middle nitrogen will give its electrons to the carbon and effectively leave. So what we get is the carbon has a negative charge and the two nitrogens are triple bonded to each other. And this will become nitrogen gas, obviously, N2 diatomic nitrogen gas, and it will bubble out of the solution, meaning it's no longer available to react. So if you imagine this is an equilibrium process, as we form the nitrogen gas, it'll bubble out of the solution. So its concentration is just decreasing as it's being formed. So that will push the reaction toward completion, essentially. And then we need to protonate this alkane. So you can take a new water molecule in the solution, protonate the negative charge oxygen, and we get the alkane. So you can use this to, let's say you have a ketone like this, and you're told that you need to make something that looks like that, and you go, how do I get rid of the ketone there? Well, you can try reacting it with a double amine looking thing like this, and of course, as always, catalytic acid and taking water out of the solution. And when you do that first step, right, you will get and then you can do hydroxide and heat, and you will get that second step. You will essentially get rid of this entire group. So that's all the reactions with primary amines. Let's discuss secondary amines. Let me take a ketone, and let's take a ketone that is asymmetrical. Let's react this with a secondary amine. So a secondary amine would have two alkyl groups on it. And we want to use the same methods. And it's a similar mechanism as to the last one, except the end is different. That is wrong, sorry. Okay. So this will be the major product and this guy will be the minor product. Looks confusing at first, but really realize that we're essentially taking the oxygen, replacing it with nitrogen again. But now the nitrogen has two alkyl groups on it, so you have to include both of them. And the bond between the carbonyl carbon and its alpha carbon, so this would be like its alpha carbon, this would be its beta carbon, and this is the carbonyl carbon. The carbonyl beta bond is now double, so it's either this or the other one. And the other one would be minor. Now, what determines which one is major or minor? So what you can do is you can take both alpha carbons. So let's take the left side alpha carbon is blue and the right side is red. This right side alpha carbon has 2 protons, while the left one has 3 protons. The one with more protons, the double bond between that one and the carbonyl carbon will be the major product, right? And the one with 2, the one that has less, that will be the minor product. So that's how you predict the product. Now let's talk about the actual reaction and the mechanism, and I'll try and be brief with this. We don't have to spend time. But basically, the nitrogen electrons again attack the carbonyl carbon, and this oxygen becomes single bonded. Then what we need to do is similar to the last one. We first basically protonate the oxygen. So we take an amine, in this case a secondary amine, that is protonated, and we use that to protonate the oxygen. Then we use just a normal secondary amine to deprotonate the charged nitrogen atom, I should say. So the entire molecule becomes neutral now. But then what we need to do is take the electrons on the nitrogen and form the double bond between the nitrogen and get the oxygen to leave. However, you recognize that the oxygen is better protonated than deprotonated because we're in acidic conditions. We can easily protonate here. So because of that reason, we take a protonated amine and we use it to deprotonate. Well, we use it to protonate the oxygen. So this guy will come and take the hydrogen proton. This becomes OH2, which is effectively water, and then this will become a normal nitrogen, and he will try and form a double bond, and the water will leave, leading to this. And again, we take the water out of the solution as it forms so that the equilibrium shifts this direction. Next, what we need to do is we have a couple of options. Remember the alpha carbons again. Alpha carbon here and alpha carbon here. We have the option of taking one of the alpha hydrogens. So here we have 3 alpha hydrogens, and here we have 2 alpha hydrogens. What needs to happen is that an amine needs to come in, use its electrons, deprotonate one of these hydrogens, and then the bond will become over here to form that double bond. Then this double bond between the nitrogen goes up to the nitrogen. You could either do that, or you can alternatively take one of the other hydrogens and form the other product. Now, let's explore the outcomes of each one. If we use one of the blue protons, we will get a product like this. If we use a blue proton. If we use a red proton, we will get an outcome that looks like that. Now, which one is better? When you look at the product, you would think that actually this would be the major product, because in terms of alkenes, you know, it's 1, 2, 3, it's tetrasubstituted, right? But this one is only disubstituted. So you'd think that the tetrasubstituted one would be more stable. And it is more stable. And that's an argument from thermodynamics, meaning we want to make the more stable product. However, the rate of that reaction to make this is slower for the reason that when you want to take a red proton away, we only have 2 red protons, but we have 3 blue protons. So we actually want to deprotonate this one as the major product because there's simply more protons to take. So the reaction will proceed faster, right? You can almost imagine it as a concentration of one of the reactants is higher. So while we do form the more stable product if we take one of these guys, that reaction is slower than taking one of these guys, so this will happen more often. Therefore, this will be the major product. So this is major, and this other one will be the minor product. Alright, now let's do a few more problems of just predicting product with this, so we get familiar with how to do that, and then we will end the video. So let's explore, let's say we have an aldehyde and we react it with, let's make one of these an ethyl group. Try and predict the product of this one. So here's what I'm going to do. That's going to be the product. And notice how we cannot form a double bond on the other side. There's no second minor product because this other side of it has no alpha carbon, therefore it has no alpha protons. This hydrogen here is not an alpha proton because an alpha proton has to be connected to the alpha carbon. This is an alpha carbon, and that's an alpha proton. And you actually have 3 of them in this case. The alpha protons have to be connected to the alpha carbon. However, if you don't have an alpha carbon, the proton is attached to the carbonyl carbon, which is different than being attached to this carbon. So with aldehydes, you can only form one product like this. Now let's explore another one. Let's say that we have, and we react it with, let's make both of these ethyl groups, and let's do catalytic acid, and let's do taking water out of the solution. Try and predict the products of this reaction, or the product if you think there's only one. So once again, this right side carbon, this alpha carbon, it doesn't have any protons on it. It doesn't have any hydrogens because it has 1, 2, 3, 4 bonds already. It can't have a 5th bond. Carbons only have max of 4 bonds. So that alpha carbon has no protons, therefore you can't be protonated to form a double bond there. Instead, the double bond always has to go on the other alpha carbon, which does have protons. Has 2 in this case. Alright. But let's talk about an example where both of them do have alpha carbons. So let's do one where we have this and we have this, and we react it with simple amine. So try to predict the products of this one, and try and determine which product is minor and which one is major. So one product will have the double bond on the right side carbon and one on the left side carbon. This one will be the major product, and this one will be the minor product. Again, the way we know this is because, let's change the colors slightly so I can demonstrate a point. So this one, let's say that one is major. It's not how you use the right major. And this one is, well, this one should be on the other carbon. So the minor product forms minor because in order to form it, you have to take away a proton on here, but you only have one. But the major product, you have actually two protons you can take off, right? So for example, when this is reacting with the amine can take two of these guys, potentially, which means it's faster. But it can only take one of these, so it's slower. So this one becomes minor, the other becomes major. So the rate of the reaction is more significant in this case than the stability of the product. So that's it. I recommend that you practice the mechanisms. Keep in mind those principles we mentioned. And again, let me go over those principles again with you. So let's begin here. Right. This principle applies to both reactions. When you have a nitrogen nucleophile, like a primary or secondary amine, you don't need to protonate the ketone first. You can just attack it straight, and then once you form this intermediate, you need to deprotonate the nitrogen and protonate the oxygen twice, so that when you want to keep the nitrogen double bonded to this carbon and to have the oxygen leave, you can have a neutral nitrogen which can have electrons, right, so that it can have lone pairs that can attack the carbon with, and then you want your oxygen to have protons so that it can leave easily as a water molecule. So understanding that stability pattern will help you to write the mechanism every time. And then with predicting products, for primary amines, you simply replace the nitrogen with replace the oxygen with the nitrogen and put the group that was attached to that nitrogen onto the product. And that can either be an ethyl group, an alkyl group, or a hydroxyl, or another amine. And when you have another amine, you can react that with hydroxide and heat and simply get an alkane. And then when you have secondary amines, you will form a major product where the double bond is between the carbonyl carbon and the alpha carbon with more protons. This one has 3, and then this one only has 2, so it's a minor product. And that's basically the whole thing with nitrogen nucleophiles. So hope this was helpful, and thank you for watching.